Hello, welcome to Convergent Dialogues. This is Xavier Bonilla. On this episode, I am honored and privileged to be joined with Steven Koonin. Steven is at the New York University Stern School of Business as Professor of Information, Operations, and Management Sciences. He's also the director of NYU's New Center for Urban Science and Progress. Steven has a PhD in theoretical physics from MIT. He has previously served as Undersecretary for Science at the U.S. Department of Energy from 2009 until 2011 under the Obama administration. He was also BP's chief scientist, and he has won many awards: the George Green Prize for Creative Scholarship at Caltech, National Science Foundation Graduate Fellowship. He's also been the Department of Energy's Ernest Orlando Lawrence Award, and he is a part of many professional societies, which include the American Physical Society, American Association of the Advancement of Sciences, American Academy of Arts and Sciences, and a member of the Council on Foreign Relations and the U.S. National Academy of Sciences. He is obviously well established in his field, and he has done much research, both on the research side of things in physics, and then also done plenty of work within public policy. He is the author of the most recent book entitled Unsettled: What Climate Science Tells Us, What It Doesn't, and Why It Matters. And that's what we talk about in this conversation. We start by talking about how are we able to trust the quote-unquote science on climate change from various institutions and from published data. We talk about the differences between weather and climate. We talk about the importance of our oceans for the planet, radiative equilibrium, and greenhouse gases. We talk about some of the data that we know about carbon. We talk about various forms of energy, such as fossil fuels, clean energy, nuclear. We discuss rising temperatures, increased precipitation, rising sea levels. We talk about how much responsibility do humans have on the changing climate. This is something that sparks a lot of debate. And we talk about what are the most balanced responses to tackling climate change. I greatly enjoyed this conversation with Steven. He's, ruffles a few feathers in some communities. And my reading of his book and of talking with him is that he is very honest and a good faith actor here. He is trying to understand the data, to understand the implications. I don't think he's trying to be controversial at all. And while he has some things that go against the grain of sorts, he is trying his best to look at the data as accurately as possible. Obviously, a warming planet is a big problem, and the fact that it's happening very quickly is a big problem. But as Steven talks about in the conversation and in his book, we have to talk about the data honestly in order to have really, really good solutions for some of these problems that the whole planet is facing. So this is a really important conversation. I hope that listeners get a lot out of it, do some their own thinking on some of these things. And now I bring you Steven Koonin. I'm here with Steven Koonin. Steven, thank you so much for coming on the podcast. I'm greatly looking forward to talking to you.
Great talking with you.
Yeah. So before we get into your book and what you've been writing about, why don't you tell folks who you are, a little bit of your background, and what you're doing now?
Okay, so let me just start chronologically. I grew up in Brooklyn, New York, educated in public schools, undergrad at Caltech. I knew I wanted to be a physicist before I knew what it was called. Did my PhD at MIT, and then back to Caltech for 30 years as a professor. The last 9 of those years as the Institute's provost, second in command. And then kind of got bored with academia and got approached by BP, the oil company, to be chief scientist. And that was a great adventure, learning about the private sector and learning about energy. I was brought there not to help them find oil and gas, but to help them figure out what beyond petroleum really meant. And then my friend Steve Chu became Secretary of Energy in the first Obama administration and asked me to help out as Undersecretary for Science. So I was basically the chief scientist for the Department of Energy. Did that for 2.5 years, and then decided I wanted to go study cities as a scientist. So back to New York at New York University, started a Center for Urban Science and Progress. Did that for 6 years, and for the last 3 or 4 years, I've been focusing back on climate and energy issues.
That's quite the CV there. That's all good stuff.
I've had a lot of fun. I mean, that's maybe one of the secrets of being a scientist is it's really a lot of fun, and you do it anyway, even if you didn't get paid to do it.
No, that's great. It's quite a lot of stuff that you've done. You mentioned cities. Are you familiar with Jeffrey West? He's
Oh, I do know Jeff West. I knew Jeff West when he was a physicist doing electron scattering.
Yeah.
Okay, so he and I go back quite a long way.
I had a very nice and very good conversation with him a couple months ago, and we talked about scale and cities, and he's marvelous.
Stuff.
He's marvelous.
Wonderful.
He's a wonderful guy. Yeah. Well, you've written a book, the newest book called Unsettled: What Climate Science Tells Us, What It Doesn't, and Why It Matters. And my understanding is that you've pissed a few people off with this book. Some people are upset at you.
I have, and well, so be it. I just felt I needed, given what I saw as a disconnect between what was being discussed in the media and political circles and what the actual scientific reports said, I needed to try to set people right. Not because I want anything to happen in one direction or another, but just I feel as a scientist and a science advisor, it's my responsibility to get a clear, unbiased, and transparent portrayal of what we know and what we don't know.
Yeah, I think that's right. I mean, I guess the first question out the gate is, many people talk about the science, right? And they talk about, in reference to climate change, and how did this become politicized, and how do we come to this environment in which we're in now, where, if you say anything against the, kind of the party line, you're going to get a lot of scrutiny. How can we have more balanced ways to navigate the conversation around climate change?
The science, as opposed to climate science, became institutionalized when the UN established what's called the Intergovernmental Panel on Climate Change, which is an exercise once every 7 years or so to produce a report. They've just released their 6th report. And this is a big international group of scientists. It's different every time. That is meant to survey, assess, and distill the science for non-experts. And they actually, when you read the reports, they're not terrible. They're actually not bad. But when you get to the summaries of the reports for policymakers, the SPMs as they're called, and then the translation of that by the media, things get terribly distorted. And I think there are many players in that distortion. The media love drama. If it leads, it leads.
Right.
What kind of story is there to say nothing's much happening with the climate, which is true in many dimensions? And then the politicians. One of my favorite lines about politicians is from H.L. Mencken in the 1920s, who said, and I won't get it exactly right, but something like, the purpose of politics is to keep the electorate alarmed by a series of mostly imaginary hobgoblins so that they'll be clamoring to be led to safety. And you see that play out, obviously, in climate, but also in immigration, at the missile gap, if you go back to the 60s, et cetera, et cetera. Sometimes there's some truth in all of this, but oftentimes it is so terribly exaggerated in order to motivate people, which is, of course, what the politicians are supposed to be doing.
Yeah, I'll come back to motivation in a bit, but you're mentioning, yes, the IPCC, and then I think you also mentioned the NCA. So it's not that necessarily what you're saying is the problem is that we can't trust some of the reports. It's usually how it's getting distilled or translated into the media or other types of groups that are trying to advocate one way or the other. And that's where it starts to it's kind of like a game of telephone. By the time you get to the end of it, it's not the same as it was initially. Is that about right?
I think that the game of telephone is a metaphor I use often. Thank you for mentioning it. Let me just give you one concrete example. When the first of three parts of the latest IPCC report was released in August of 2021, it's 3,949 pages, and it took 200 scientists 3 years to write. And it's terribly dense and detailed. And as I said, it's not a terrible summary of the science. But when it came out, the Secretary General of the UN, Antonio Guterres, said, this is code red for humanity. And so you can search the report for words like climate crisis, climate catastrophe, existential threat, and so on. And you actually find none of them except once you find the words climate crisis. And that's not a scientific finding, but instead is a statement about how the U.S. media have overhyped the situation. And so, it's a great platform for Mr. Guterres, for Ambassador Kerry, pick your favorite politician, to stand upon, because nobody ever actually reads the reports.
So it reminds me of the ACA bill, where it was like 2,700 pages and people haven't read it. It's like the HIPAA bill, which people still, I know people, I think in some programs in law, they'll just take a piece of the HIPAA and just emphasize that piece because it's so large. And so it sounds a little bit similar to that.
One of the things I didn't put in the book, but I often talk about, is that there is an economics professor at MIT, Jonathan Gruber, who was advising the government, was one of the principal architects of the ACA. And he said in a conference after it was all over, he recorded on video, saying the only reason we could get a key provision passed was based on the fundamental economic ignorance of the American public. And, that is so contrary to the ethos that I was taught as a scientific advisor. He's still got a job, but we should coin a verb called to Gruberize.
Yeah, this is kind of these things where, the importance of doing science is that you're able to then eventually explain it to people in a way that's accurate, but intelligible. And so I guess one of the ways to do that is explaining the difference here between climate and weather. I hear people get this confused to this day all the time. For example, I mean, this will be a little dated, but, it's the middle of April and yesterday we had snow. And people are like, oh my God, they're losing their minds. It must be climate change, right? And so people still get this confused. So how do you usually explain this? Because I think it's a super important point for people.
So there's an aphorism that dates back, I think, to the early 20th or 19th century, that climate is what you expect, but weather is what you get. So climate is an average. Officially, it's a 30-year average of the weather, not only the averages, but the average fluctuations and so on. You're supposed to look back over 30 years because, as you say, the weather, or even from year to year, things vary a lot. And you can get fooled by a fluctuation of a few years saying, oh my God, it's getting warmer, or it's snowing more, or whatever. But if you take the longer term view, you see it's just a bump in what is otherwise a rather normal process.
So it sounds like it's mostly looking about the trend lines as opposed to kind of the spikes, low or high.
So the trend lines are, of course, how things are changing. And we're talking about climate change. And so it's worth making another distinction. When you say climate change, everybody thinks human influences and rising carbon dioxide, methane, whatever. Whereas the climate changes on its own perfectly fine, and it does so a lot when you look at the historical records. We can talk about some of those. They're interesting. And so when the politicians say climate change, they mean human influences, but actually they're conflating it with the natural variation of the climate system itself.
Yeah. Yeah, I've talked to a handful of people on the podcast now about that do earth sciences or geology, or they do paleontology, and at different periods on the Earth, the climate has always been changing, right? I mean, we're technically still at the end of an ice age, et cetera. There's always different changes within the climate. But yes, I think most people are referencing, how much are humans' contribution to that rapid change in the climate. One of the critical pieces for a warming climate is the oceans. Maybe could you just tell us a little bit why the oceans are super critical here for being a kind of nesting ground of sorts for how the climate continues to warm?
Yeah. So, I mean, we can think about the climate system as basically two big pieces. One is the atmosphere and the other is the ocean. There's also the ice and so on. But for this purpose, let's just talk about ocean and atmosphere. Mm-hmm. The timescales on which the atmosphere changes are pretty rapid. We see fronts go through, we see storms come and go, and the coherence time, if you like, of the weather at any one place is a couple of days. Mm-hmm. Whereas the timescales in the ocean are decades to centuries. In other words, it takes the currents sometimes as much as 1,000 years to circulate around the globe. The changes are much slower. Moreover, as the planet absorbs heat, and we're pretty sure it's absorbing a small fraction of the heat that the sun gives us, as the planet absorbs heat, the great bulk of it, more than 90%, goes into the ocean. And so the ocean is the long-term memory of the climate system, but it drives the atmosphere, and conversely, the atmosphere affects the surface currents.
Yeah, well, as you're illustrating, the oceans are super, super important. One of the things that you discuss in the book is radiative equilibrium, right? Or more how greenhouse gases don't trap, as most people think of it, but more of a catch and release program. Maybe discuss that a little bit.
Yeah. So the temperature of the Earth is set by a balance between the sunlight that it absorbs, and it doesn't absorb all the sunlight. It actually absorbs only about 70% of it. The rest gets reflected. And then the heat that it sends back into space. And those have to be balanced to within a fraction of a percent, because if they weren't, the planet would be heating up tremendously rapidly, and we don't see that. And so they're pretty much in balance. Now, we can't measure precisely enough the reflected sunlight, the absorbed sunlight, and the reflected heat to be able to say how much it's out of whack.
Right.
But the way in which we do that is by measuring how fast the oceans are warming up. And we do see the oceans warm. Yeah. But it's, let me see if I can put it in, it's maybe 1/4% of the sunlight that's involved, so it's very slow. But that is what radiative equilibrium is. Now, when we look at the heat coming out from the ground, it has to pass through the atmosphere. And that atmosphere, because of carbon dioxide, but more importantly, water vapor, can intercept that heat. Actually, most of it. It intercepts about 90% of it. But it can't stay trapped. It can't stay intercepted. Because otherwise, again, the planet would be heating up really fast. So it rattles around in the molecules of the atmosphere and basically finds its way back out into space again. And it is that balance between the total amount of heat coming out and the sunlight that gets absorbed that sets the temperature of the planet.
Yeah, that's super helpful. One of the things that people discuss a lot here is about CO2. Right. And so you talk about a few gases in the book. You talk about nitrogen, oxygen, carbon, and all of those are kind of these important ingredients for climate on the Earth. How much do we know that carbon is naturally emitting, and how much is human involvement? I can imagine that's very, very difficult to kind of pinpoint. But what are our best guesstimates on this?
So the atmosphere contains carbon almost entirely through carbon dioxide. So there's a little bit in methane, which is a different molecule. It's carbon and hydrogen as opposed to carbon and oxygen in carbon dioxide. And the principal issue is the carbon dioxide. And the carbon dioxide, or more generally the carbon in various forms, flows up and back between the Earth's surface and the atmosphere with the seasons at about 200 billion tons a year. So 200 billion tons go up into the atmosphere, and then another 200 billion tons, almost in balance, come down every year. We humans are digging out about 9 tons of carbon a year in the form of oil, gas, and coal, and a little bit of deforestation, and are putting it into that interchange, that cycle of up and down. So it's 9 compared to the 200. And that's gradually building up. Not all of the 9 stays up there, some of it gets absorbed, but it's gradually building up, and it's the accumulation of that carbon dioxide that is affecting the climate.
So it's the accumulation over years of time?
Yes, absolutely. The lifetime of carbon in the system, in the up and down, it depends how you measure it, but it's at least 100 years, and some people would say many 100 years. And so it stays up there. It just accumulates. That's in contrast to methane, which actually lives only about 12 years. It gets destroyed and gets converted to carbon dioxide, but it's only a small addition, very small addition to the carbon dioxide that we're adding from burning fossil fuels.
You also mentioned that there are natural forces, as you're saying, kind of this 200 tons of the volcanoes, the sun's intensity, that are contributing to climate change. What are, I guess, kind of the natural pieces of this? And then I'll ask you about fossil fuels.
So there is the sun's intensity, which has been measured, and at least the intensity part of it is thought to be a very minor factor in the climate, namely the intensity of the light. But the sun influences the Earth in other ways as well.
Sure.
Cosmic rays, most importantly. And I think the jury is still somewhat out on whether the sun might have a more direct influence than the sunlight. It doesn't have to be much. It's fractions of a percent is all it takes to have it affect the size of CO2. Another one is aerosols. So you mentioned the volcanoes. The volcanoes go off, like Pinatubo. The aerosols, the particles that they create, stay up in the stratosphere for a couple of years and shield the planet a little bit. And so drop the temperature. It's measurable. We can see it. I think much more important are the natural variations in the climate system. We're coming out of the Little Ice Age. It started in the 1600s and thought to be over by about 1850. But exactly why that happened, we don't understand. And that these long-term, multi-decades to century variations in the climate system are frankly ill understood. The short-term ones, like El Nino, we understand pretty well now. But for example, there's a phenomena in the Atlantic called the Atlantic multi-decadal oscillation, which extends over 70 years. And so if you're measuring something now and you say, it's doing something, you just wait 40 years and it's doing the opposite. And whether it's melting Greenland or it's hurricanes, these or sea level rise, these things influence, these oscillations, influence the climate variables that we measure on multi-decadal scales. And we had better understand them in order to confidently attribute changes that we see to human influences.
Yeah, certainly. Well, one of the things that gets talked about a lot is fossil fuels. People talk a lot about fossil fuels. What is the data we have on that? And explain what it actually is, what's the data, and what to make of it.
So fossil fuels are just that. They are fossilized organic matter, plants. We used to joke in BP that they were dead dinosaurs, but not really. Okay. And they form by the organic matter getting drawn into the earth and then subject to heat and pressure. They're under the ground, and if you cook it Only a little bit it turns into coal. If you cook it a lot more, it'll turn into oil, and then it kind of migrate into a reservoir. Or if you cook it a lot, it'll turn into gas. And this is extinct carbon that has been withdrawn from this ocean atmosphere or surface atmosphere cycle and has been buried away. And in some ways, you can think about it as stored sunlight, because after all, it was the sunlight that made the plants grow and created the organic matter that was buried. It's wonderful stuff from a energy point of view. It's very concentrated energy. We have learned how to use it in very convenient ways, whether it's oil for gasoline and diesel, or whether it's natural gas for generated electrical power, or heating our homes. And so, if you didn't have CO2, it's actually really good stuff. And so the question is, how much catastrophe do you think we're facing by filling up the atmosphere with a little bit more carbon dioxide? That's the question.
Yeah. Well, most people will say, I mean, I know that one of the things in the first term of the Obama administration, right, which was the whole idea of clean energy. Everything it was solar and wind and all these different types of ways of getting alternative forms of energy, because we didn't want to be drilling into the earth with fracking or offshore or things like that. And some people now talk about the amount of nuclear energy we could get. So there's just basically multiple forms or multiple ways we can get energy that we need for the planet. Is there a way in which, I guess you could say, not that one's more superior than the other, but is there one that is very good and that can be less destructive on the planet? I mean, is it totally taboo to be like, fossil fuels are good or nuclear? Like, these all have their value and their merit, right? Obviously, if there's an excess or if you're abusing things, but how do we kind of understand that kind of balance of sorts?
Yeah. So one of my colleagues once taught me that the only humans who don't pollute are dead ones, and that's not even obvious. Right? So, that anything of the scale of energy, which is an enormous enterprise, is going to have some environmental impact.
Sure.
And so CO2, aerosols from dirty coal, which we've learned how to clean up largely. The manufacture of batteries creates local pollution and leaves behind things you have to recycle in some way. So everything will create pollution, and it's a question of what poison do you want to take. But as we do that, I mean, there are some desiderata for energy that it's important to keep in mind. I think the most important one is there are 3, 4, depending on how you count, billion people who do not have adequate energy. And right now, the most reliable and convenient way of getting them that energy is fossil fuels. And in fact, 80% of the world's energy today comes from fossil fuels. So that's the first thing to think about. The second is, here in the developed world, we want our energy to be reliable. And we've seen over the last couple months with the Ukrainian situation how energy security is so important. The second thing, we want it to be affordable.
Sure.
And the third is we want it to be clean in a local sense. And so the local pollution, mercury, sulfur, but also greenhouse gases, CO2, which is a global issue. So you put all of that together, you can't run an energy system on just wind and solar, because wind and solar only generate when the weather allows them to generate. Namely, it's sunny or it's windy. There are many times when there's no sun and no wind. And Europe, as you may know, was becalmed, and it's not a particularly sunny place to begin with, for several weeks. And so you had better have some kind of backup in order to handle those several week periods when solar and wind don't generate. And that's what is the most expensive thing in creating a high renewable electrical grid. You got to pay for the backup. And it's generally 3-4 times more expensive than the wind and solar itself.
Mm. And what about nuclear energy? People like to talk about this as well. I mean, obviously we have Chernobyl, which was a huge, I mean, it was terrible. There have been other accidents, but that's obviously the big one people know. That's always the worry of, well, wait a minute, we know how to use nuclear energy, and maybe it's a little bit cheaper in some ways, but oof, man, that's it's kind of a Russian roulette kind of thing there.
Right. So full disclosure, I'm a nuclear physicist, and nuclei are my friend and have been for 50 years.
Sure.
But you wouldn't ask me to design a nuclear power plant. I can tell you how fission works, but not a nuclear power plant. So, first of all, the high-level statement is, if the world wants to significantly reduce its greenhouse gas emissions while still providing adequate energy, I think fission, nuclear power, has got to be a major part of the picture. Right now, it provides 19% of U.S. electricity with no emissions. Base load, namely, it's running all the time in contrast to wind and solar. However, we need to work on it. And in particular, we need to reduce the size of the reactors that we build. Right now, we build reactors that produce about 1 gigawatt of electricity. That's a lot of money to put down. It's like $10 billion to put down and build the plant.
That's a lot, yeah.
And then you have to pay it off over 30 or 40 years. People are trying to build reactors that are about a tenth the size, so 100 megawatts. If you can build them in a factory, you don't have to go through as much certification every time you build it. You can build them in the factory, put them on a railroad car or a flatbed truck, cart them to the site, and then install the first one and use the cash flow from it to install the second one, and so on, and make it much more easy financially to do that, and also regulatorily. People hope to get the first one of those in the ground in the next several years, and we'll see whether they can bring the cost down enough to make it competitive.
It sounds like for me personally, it sounds like there should be, at the very least, an all-hands approach. Obviously, we want to protect the planet and the environment and not be wasteful or in excess. But I really get a little bit worried when people start saying, this is completely off the table, or this is completely off, or we should only do this. Absolutes don't typically work. It's a big planet, 8 billion people, and as you said, 3 to 4 billion, have energy limitations. And so, I think we have to maybe just see, can we use everything on the menu and not just one or two things.
And often it comes from an ignorance. And I don't say that in a pejorative way, just in a factual way. I teach, and I'm teaching now, an energy course here at NYU to graduate level engineers and MBAs. And it's soup to nuts. We do technology, business, regulation, and so on, and all of the forms of energy. And it's amazing to see the eyes open up as we go through the course, as people start to understand the scale, the complexity, the nuance of any of these decisions. So, I think we do the world a great service if we could just promote some energy literacy.
Yeah. There's one last thing I want to ask about CO2 in terms of how we understand the rise of CO2. So you talk about 5 independent lines of evidence: so timing, size, rise in northern hemisphere, carbon isotopes, and decreasing oxygen in the atmosphere. Just tell us a little bit about why those lines of evidence are important to show the rise of carbon.
So let me go through them all, and I'm not sure I can remember them on the fly since it's a while since I read it. But let's talk about the timing, all right? So we see CO2 pretty flat at about 280 parts per million up until, over thousands of years, up until you get to the start of the Industrial Revolution. And then it starts to take off. And these days, it's up at about 420 compared to the 280 it started, and it goes up at about 2 or 2.5 parts per million. And so that's one signal. Another is the magnitude. You can add up how much carbon we have burned and how much carbon shows up in the atmosphere. And what you find is about half of it shows up in the atmosphere, and the rest of it is presumably absorbed by the plants and the oceans. The third is, there's more carbon, the concentration of carbon dioxide is slightly higher in the northern hemisphere than in the southern hemisphere. And of course, there are more people in the northern hemisphere, many more. And so the thought is that people put it up in the northern hemisphere, it stays there for a couple of years and then gradually diffuses into the southern hemisphere. And so that's another one of it. The one that's most persuasive to me is the carbon isotope story. Carbon comes in two isotopic forms that we can measure easily, carbon-12, which is the most common one, and then a little bit of carbon-13. And it turns out living things like to absorb carbon-12 more than carbon-13. And so when living things absorb that carbon, they're a little bit rich in, or they're a little bit depleted in carbon-13. They get turned into fossils and then they get burned. Putting it back up, you're putting up into the atmosphere somewhat depleted carbon, namely carbon that's deficient in carbon-13. And that's what we see in the atmosphere. The atmosphere is getting progressively lighter, a little bit more carbon-12 than carbon-13. That says that the carbon that's come out is biological in origin. And then the last one is, as we pull carbon out of the ground, it gets burned and so combines with oxygen. And so we should see the oxygen in the atmosphere go down a little bit as we burn the carbon into carbon dioxide. And in fact, we see that. The magnitude is not quite right. There's still some uncertainty about that, but it's there. Of course, we shouldn't be too worried. It's only at the part per million level or something that it's going down. And we got plenty of oxygen. We're not going to run out of breathing. But it is a good signature that we're oxidizing carbon. So all of those together suggest to many people, and believe them, that CO2 is going up because of burning fossil fuels.
Let me ask about two big things that kind of come up. So how do we measure over time all of these high temperatures, record high temperatures? We hear this all the time. And then about increased precipitation, flooding, rising sea levels. These are the things we hear all the time. So what can we say about the high temperatures and then the kind of the rising waters and precipitation?
Yeah, so if you look at, and this was one of the deceptions I identify and talk about in the book in the National Climate Assessment, at least in the U.S., record high temperatures. So what was the maximum temperature reached at a given station in a year? And then you can plot that. Or you can say, how many record daily highs did I get? Or record daily lows? And what you find is that the record highs are not getting any higher or any more common. They're about the same as they were at the beginning of the 20th century.
So we're not seeing 150 degrees Fahrenheit, days on the planet. We're not seeing 135 or 40 necessarily. Usually about 120-ish is the highest usually.
Is the highest you get. And the highs are, so as I said, are not becoming more high or more frequent, but the lows are becoming less low. And the lowest temperatures are warming. And this is consistent with what we see around the globe, namely the coldest or the coolest temperatures are becoming warmer faster than the warmer temperatures are becoming warmer. And so there's a little bit of a compression, if you like, in the range. If you wanted to be snide, you can say the climate is getting milder. Namely, the extremes are disappearing. So that's one fact about the temperatures. And there was, I think, a deliberate misrepresentation of that in the National Climate Assessment that I go through in the book. With respect to precipitation, we do see some increase of intense precipitation over land. Precipitation is very hard to measure because it's kind of spotty. You can get a really big downpour one place and not. But particularly here in the Northeast, we're seeing somewhat more intense rainstorms. Although, it's not always true. So last September, we had a record 1 hour precipitation in Central Park. And so I started to look up the precipitation record, and it's hard to get 1 hour records back before 1960. It's kind of hard to measure that when you think about it. But they can measure, and they did measure 1 day records. And so the one day in which we had the 1 hour record back in September of 2021, that was only the fifth rainiest day on record in Central Park. There were four others, and the rainiest one was actually in 1879.
No.
So we tend to forget a lot about weather, and you need precise records to look for these small changes associated with climate. I'll give you another example. In 1955, there was a big drought in the Midwest. And one of the national magazines, I think Times, said, this drought will be long remembered. Does anybody remember the 1955 drought? No? So, we pay attention to weather. That's what we get. But you got to take this long-term perspective. We can talk about sea level rise if you want to do that. That's kind of interesting.
Yeah, I was going to ask also about increased flooding and rising sea levels as well that hit many cities. People say that Miami's going to be underwater and New Orleans going to be underwater and all these things. Now I think that maybe it's true that there are some islands that are that people live on that are definitely going under. I think there's been a few examples of that, and that might increase. But how do we discuss that?
So as a scientist, I first go to the data, and but the sea level is rising. In some places, it's actually receding. But sea level is rising at a given location because of two things. One is that the global ocean level is going up because some of the ice is melting from the glaciers, or the water's just getting warmer and expanding. But then it's also going up because the land is sinking. And you can look at different places and you can try to tease out how much is due to subsidence and how much is due to the global ocean truly rising. Let me just give you one example. I live some of the time in Manhattan, and there's been a tide gauge at the tip of Manhattan, the southern tip, the Battery, as it's called, since about 1850. And we've got a pretty good record then of the average height of the ocean, averaged over the tides and the seasons and so on, for about 160 years, 70 years. And if you just draw a straight line, it's been going up at 2.88 millimeters a year. So if I translate that into more familiar units for most people, that's less than a foot a century. So the sea level has been going up less than a foot a century at the Battery. And that's true at most places, including Miami, where the land is sinking more than the ocean is rising. But you can ask, what about the shorter term trends? If I break it into 30-year trends, what's it doing? And what you discover is it oscillates. In one decade, it was down at 1.5 millimeters a year, and then 30 years later, it was up at 5 millimeters a year. So it goes up and down due to these cycles in the Atlantic. Now, it's currently at a high, but it looks like it's coming down again. I got a picture in the book. You can see that. Now, the models that are used to project climates say that in the next 30 years, it's going to go up a foot. In 30 years, that's 3 times as much as it has been rising, or 3 times as rapidly as been rising over the last many years. The IPCC at least had the honesty to say there are big uncertainties in that. And it could go up a foot, it could go up a couple inches. NOAA, the U.S. government agency for oceans and atmospheres, put out a report a few months ago that said it's guaranteed to go up a foot in the next 30 years. Well, I can tell you, we'll see. And we'll see pretty quickly if that happens. All right. Yeah. So oceans are pretty hard to predict.
Yeah. The biggest question. So I think much of what, if anyone that's been listening up to this point will say, okay, Steve, I'm with you on a lot of this. Okay, we got to have a all hands approach on these things. Yes, maybe some of this stuff is not as catastrophic as many people think. Obviously, we believe that climate's warming or all these things are happening. Fine. But where people argue on this, on where they argue politically, but I think just maybe also with with people in generally, is how much of this is our fault. right? How much of this is human involvement, right? And so for all of these things we've discussed, right, there's things that are, there's deforestation, droughts, fires, flooding, all the things we've discussed, CO2, methane, etc. How much of this is the biggest thing is it's happening too fast in such a short time because of humans, because of waste, because of all the different things we're doing. How much can we say? What can we say confidently, and what is more questionable about the involvement of humans for the contributing to the rapid change in climate?
Right. So let's distinguish maybe first the changes in the climate itself from some of the phenomena like forest fires or even floods that we have actually some control over by the way we build dams or the way we do forestry and so on. So let me put those aside.
Sure.
Let's just talk about the climate variables themselves. Two things to understand. One is that human influences have been growing. If you go back to 1930, they were less than 1/5 of what they are today. And, you go back to 1950 and maybe they were a quarter or something like that. And so if you're going to say it's humans, it's got to be something that you see in the last 60 or 70 years that you didn't see before. Either something happens more frequently or something bigger or smaller happens and so on. And for many of the things we see, it's happened before. Like the precipitation we were just talking about. Sea level rise was rising about as rapidly 80 years ago as it is now. Greenland was melting about as rapidly 80 years ago as it is now, and so on. So the challenge is to untangle some of those.
Yeah.
In terms of the gross properties of the climate system, the global temperature, which is a common measure, the IPCC says it's all humans. And I and many others have said, well, what about the natural variation? And they say, well, they average out in the models. They kind of ignore them. And there are parts of the historical record that the models don't produce that must be natural variation. And so I would say it's probably half, maybe about that much. I'd be willing to understand it's all, but not been proven yet. So that's where I stand on how big an influence humans have. But, a maybe even bigger bottom line question is how much does the projected change influence the economy or ecosystems? Right? If it were warming, and it would, actually some people think modest warming is beneficial. I think we could understand why that might be. How much is it going to impact things? And there, the IPCC and the National Climate Assessment says that a warming of several degrees, more than Paris is trying to limit things to, would have a net economic impact of a few percent 70 years from now. So, it's an issue, at least in terms of net economic impact, but it's certainly not a catastrophe.
Why would the IPCC say it's all? I mean, nothing's all, of one thing. Why would they say that? They
tune the models, and the models, of course, disagree with one another a lot, and also disagree with the actual record, each individual model. But when you average them all together, it actually fits the recent temperature record very well. And they say, so we understand it. It's not natural. But if you go back further, before 1950, they got some problems in trying to reproduce the observations that says there must be natural variability. We know that there's natural variability because we see it in longer term records.
What about the many of the things that we have been doing for 40, 50 years now? I mean, I'm not that old. When I was younger, people didn't recycle. Now everybody recycles, right? At least in the Western world, there's so many things that we've done in cities and in the Western world to reduce our carbon footprint, all that stuff, all those campaigns. And my question is of course there are things that, are going to keep happening, but has that made a dent in anything?
No.
I mean, that's what I always wonder with these things.
So the recycling is about local pollution, all right? And actually, only a very small part of the carbon goes into producing plastics for example, very small. The great bulk of our emissions come from electrical power production and secondarily from transport and oil, and also from agriculture. Agriculture, methane gets generated in rice paddies, from cattle. CO2 is produced when we make fertilizer. And so those are the big things. It's disappointing to tell people that your own individual actions don't really have any effect at all. But if you really wanted to have some effect on this, you should vote. Okay? But the difference is the people in India or China, if they could vote, would probably vote very differently than we in the developed world would, because they're facing an immediate issue of not having the energy. Whereas this is a much longer term issue that, frankly, I believe we will be able to adapt to.
Yeah. So a few things on the, I guess, the response here, right? So we've kind of been dancing around it and stuff. So I guess my first question is, do people need a background in physical science or earth sciences to fully understand the data, right? If somebody says, Steve, I don't have a PhD in physical sciences, where can I go to get a really good balanced summary to understand climate and what's going on?
So the expected answer is go read my book, all right? and I actually tried to do that, which was to make the science accessible to non-experts, people who could just read graphs, basically. I think most people can do that. I think if you, the textbooks are probably too, the American Chemical Society has got a pretty good set of web pages that go through the basic science. The problem is they don't give a realistic portrayal of natural variability, of the deficiencies of the models, the fact that the economic projections are minimal, the fact that sea level is only rising at a foot a century, things of that sort. So the basic science, if you really want to learn it, you can find, as I said, places to do that. But I think for most people, it's kind of the more direct the impacts, sea level rise, storms, and so on. Most people don't know that it's very hard to find any long-term trend in hurricanes over almost 100 years. They go up and down, and some years are more than others, but only very recently have we seen the hint of a long-term trend, and even that is in dispute at the moment. So the media and most of the popular literature just sensationalize this stuff, where you can go read the report, as I point to people in the book to, you see, there's no trend in hurricanes.
Yeah, this is very hard for people. I mean, if trying to have this conversation of this is, again, we kind of mentioned in the beginning, is there's plenty of, again, politicians and people in Hollywood and, whatever, all of these folks are really saying one thing, which I think is true. So I want to be clear. Obviously, I think the climate is changing for various reasons. I definitely can see that there is human involvement. I definitely think we should be, in some ways, I think, responsible for what we're consuming and putting out. I'm not saying any of that stuff, but that we shouldn't do any of that. But it is kind of a thing where it becomes difficult to kind of wade through what is what's there and what's not. One question here is the one, when I was reading your book and at the end of it, I was trying to kind of do the kind of devil's advocate piece of this. And I was like, would people take climate change or what's going on the planet seriously if we just use terms like, well, maybe, possibly, it could happen? Like, do you feel that, the right tone to get people's attention is it has to be a little bit elevated, but not exaggerated too much? I mean, that's just kind of how things move, right? If people are like, well, it's going to happen eventually, no one's going to do anything. How do we kind of strike that?
And I would say, as a scientist, not my job.
Right.
My job is to bring the facts to and other scientists, bring the facts to the table with all of the uncertainties and certainties, because I don't know what the right answer is. Yeah. And the scientists in particular are probably pretty poor at telling you what the right answer is, because the right answer involves a balance. Yeah. And that balance involves values.
Mm-hmm.
How much do you care about 4 billion people? How much do you care about the cost of energy versus the environment? How much do you care about intergenerational equity? If we were facing a certain catastrophe, I think the answer would probably be, well, we got to reduce and we got to do it fast.
Mm-hmm.
On the other hand, we're not facing certain catastrophe.
Mm-hmm.
In fact, it probably, again, if you believe the IPCC, going to be a bump in the road.
Mm.
And so you've got to, as a scientist, I think I got to bring the facts to the table, expose the facts in the official reports, and then let the politicians and the media and everybody else have this values discussion. And the values, are all over the map because, again, if you're sitting in India, you got a different set of values than sitting here comfortably in the U.S. or Europe.
Well, and that's just it. I mean, you take a place like India with 1.3, 1.4 billion people, just there's size and scale and so many things. It's very impoverished in many big parts of the country. It's really, really difficult. And you're talking about values. It's interesting because, I think the Carter administration tried to do some form of cap and trade, didn't really go that far. I know that was sort of kind of flirted with in the first term of the Obama administration. That didn't go far. And, it's one of those things where if people were really serious, if they really, and I just think there's not enough people that would do that because at the end of the day, it's, well, I got to pay more and to use more energy.
Even if we did it, if the U.S. were to do it, the U.S. is currently 13%. Of global emissions. Right. If we went to zero, that would be wiped out by less than a decade's worth of growth in the rest of the world. Yeah. And so you got to get the whole world to come along on this. Yeah. And frankly, I don't see how that happens.
Yeah. You mentioned in the book there's a few red flags, right? In terms of, you talk about, you're just a climate denier. You talk about 97% of all scientists agree, et cetera. Maybe just expand on the red flags there and what to do about that.
So, when you read media coverage, anybody who uses the term climate denier is not talking serious science. All right. I mean, I have been called that, but, I believe what's in the reports. What am I denying? Maybe you're denying something if you call me that. Often could be as much as in so they'll take the most extreme scenario and the most sensitive model to try to scare the pants off of people. Or they'll quote, energy is full of big numbers. And they'll quote some big number out of context. So again, we talked about the U.S. The U.S. emits about 6 billion tons a year of carbon dioxide. Big number, right? But it's only 13% of the whole story. Or, they'll say this technical innovation is equivalent to taking the 1 million cars off the road. Well, there are 1 billion cars in the world. And so what is 1 million going to do for you? All right. So talking about numbers without scale is another sin that the media often commit. Another is historical context. This is the worst thing since 1970, let's say. But what about before 1970, when human influences were much smaller? So those are the kind of things I would urge people to be sensitive to.
I think some of the things that people kind of hit you with is like, well, Koonin's he's just cherry picking. He's just taking the parts of the report that he likes. And, he's not talking about all these other things about, look at all this stuff. I mean, that's, I think, where people give you the most criticism. What do you kind of say about that in general?
So I tried to stick to bottom line issues. How many storms are there? Yeah. What's the net economic impact? How fast is sea level going to rise? So I don't think that's cherry picking at all.
Sure.
And basically, if you pick enough cherries, you got the whole bunch eventually, right? So I think people the facts are what they are. All right. And this is not a simple issue. I've tried to point out some things that surprise people, but maybe more importantly, where they have been misled. And I think that should promote people, particularly the scientists who are not climate experts, to asking some harder questions about what are you really telling me?
The last question I have for you is kind of what we do about it. I think you mentioned at the end of the book how we need to adapt. That's your biggest thing. And now people may say, well, that's too passive. We can't just adapt. We got to really be aggressive to try and fix this. But what can you say are the things that we can do to combat some of these negative aspects of a changing climate, and what can we do?
So I think the first is we need to improve the science. The understanding of the climate requires long-term, precise observations of climate variables that extend over decades. We need to keep that going and do more, the deep oceans, for example. We need to understand that better. I think a second thing we need to do is to try to get a bit more honesty in how we talk about this to the general public. And, peer reviews of various kinds. I've suggested a red team exercise for the assessment report. I think then a third thing we need to do is to cancel the climate crisis. Okay? The climate crisis says we got to do things right away. And in fact, if you do things right away, that's doubly bad because you have disrupted a lot in society, but also you've deployed immature technology. And so we need to work hard to develop emissions light technologies. High on my list would be the small reactors we talked about, better carbon capture and storage, better electrical storage, big batteries or other methods so that you could use more wind and solar, which have come down in price a lot. So those are some of the things we can do. And more generally, formulate a deliberate plan that involves technology development, the economics, business regulation, that let us get there gracefully rather than the kind of all hands on deck, the house is on fire attitude that the politicians have been pushing, which, as we've seen, can be quite disruptive, if not destructive. If this administration had not been denigrating oil and gas production, we might be in a slightly better position to deal with the Ukraine-related oil and gas shocks than we are currently.
Yeah. Well, the book is called Unsettled: What Climate Science Tells Us, What It Doesn't, and Why It Matters. I think it's available everywhere. Where can people find you and all of your work and what you're up to?
So I deliberately stay away from social media because I don't think that's a very productive mode of having conversation.
Probably a good move.
I do have a Medium page.
Nice.
Steven Koonin Medium, whatever the URL is, where I have put up some of the presentations and interviews that I've done, but also have responded in detail to critics.
Nice.
That the fact checkers at Facebook who got a lot of it wrong. I could go on and on. Sure. But, at the end, this is a scientific discussion, and I've tried to respond in a scientific way. So they can find my Medium page.
Oh, that's great. That's really nice. I can't say enough thanks for coming on and talking with me. This was a really, really good conversation, and I greatly enjoyed it. So thank you so much for having the conversation.
It's a pleasure to be able to have a long, nuanced conversation.
Of course.
So
you're welcome anytime.
Thanks for having me.
Of course. Thank you.